Yeah, okay. Okay. So first of all, let me yeah, I want actually to connect Upper Macintosh and show what is there, but basically it is possible to install Govin on Upper Macintosh, and but we need to modify our scripts, and I can show where it fails right now. So let me share the screen. 1 second. Yeah, so if you look to our scripts, yeah, so people in Govin who did the port, they didn't do like standard Macintosh installer, and they didn't do Mac application. Like they just created like bunch of files. You just need to like unzip somewhere and set environment variables, and this is just fine for us. And we had a discussion in like Telegram channel with them. Just a second. So we had a discussion in a Telegram channel. So this is a discussion, and they essentially said that we need to put two environment variables. 1 second. Yeah. So if you put those two environment variables, then it's going to work. And then there is a guy, this like Charlie, whatever. So he put their code in like a Mac application. But the problem is that when you put it as a Mac application, then it asks for Rosetta Stone, which is a technology to run x86 like x86 programs. And then I asked him whether their engine runs on x86, so like ARM-based M chips, and he said that ARM-based M chips. So I suspect that this Rosetta Stone was needed only for additional software by this guy. So maybe it is not necessary. So if we look to his website, so he created a script to fix it, but probably we don't need it. So let's see what he is doing in the script. Remove quarantine, fix linking. Oh, maybe this code sign assistant, but I have no idea what this assistant is, but maybe this assistant build version home. So maybe this assistant is trying to execute x86 instructions. So something is trying to execute x86 instructions, but looks like it's not their software, but this additional software which we don't need. So the bottom line is that we need to we need to, in order to use Govin on Mac, you need to like install their stuff, and then you need to put two environment variables, and then you can just copy it into Govin directory. And then you can run our scripts, but when I try to run our scripts, what I found, if you go to steps, set up Govin, like I found that like Upper Macintosh has a little bit different find command, and their find command does not accept this option. So we need to go through the scripts, and like probably I need to go or somebody else and change this fragment of code, just rewrite a little bit. So do you have any experience in such scripting or not, like Bash scripting?
I don't have
Kieran?
much experience in Bash scripting, Yuri. I try to
Okay.
do Python. I use Python for scripting. So
Okay.
all my scripts I try to write
Yes,
in.
this is fine. This is fine. In this case, never mind, because for this kind of task, it's necessary somebody who is very well familiar with Bash to just change this code in a little bit. Yeah, but well, this is something what I want to do, because looks like there are many like students, especially, who use Upper Macintosh. And what I also found is that Govin works very, very fast on this Upper Macintosh. So its synthesis takes like literally like second for a simple example. So which is surprisingly good. Now, what I want to talk to you about is using Volley, but using Volley in a very different way. So we got homework. So recently I, together with Mike Kuskov, so we got Volley. Let me put it on a website. So we got Volley, and we just extracted some pieces of Volley. We just got Volley FPU. So if you go to open open hardware group. Yeah. So if you go to Volley FPU, so to Volley source. So we just got pieces of FPU. So if you look to this micro architecture diagram, there is this FPU execution units, right? So now if you go to source FPU, there is source code for this floating point unit, right? And there are many blocks for doing arithmetic operations. For instance, if you go to this compare block, F compare, you can see this is simply a combinational block which is doing a comparison of IEEE floating point numbers. So what I did together with Max Kudinov and Mike Kuskov is that we created a script which is used to run homework number 3, and this script so when you run Linux Mac, it looks for another script, and this script actually clones volley repository and extracts pieces from it. And then we put our oven wrappers over volley blocks. So let me first show you the script. So if you go to run Linux Mac, yeah. So if directory import original CVW does not exist, it clones the volley, and then it pre-processes it a little bit. So it copies blocks of FPU, and then it runs a bunch of set command to remove from the constructs which are not understood by Icarus Verilog. Like for instance, using packages. So if you run this script, so if you simply run a script, so okay, what was git pull. A second. Let me stop sharing screen to not record this. One second. We just need to get the token. Okay. Okay. Okay, so let me share screen again. Okay, so now if you run this script, so run Linux Mac, it will ask you, so we need to import external files in order to do soft floats, and needed files are located in Volley, so clone third-party repository from GitHub. So we press yes, and it will clone Volley into our import original directory. Okay. So what it does, it creates a directory called import, and inside it has a directory called original, and inside it has complete repo of a volley, right? And this repo in source, you have FPU, and you have this comparison module, and it has this module for fused multiply accumulate, which is a pipelined module where you're doing one stage multiply and another stage accumulate. And and you can see that once we like edit those files, so let me show you what kind of editing we are doing. For example, here we have parameter from a package, and you have this like import CVW, but because Icarus Verilog does not support everything in packages, it just supports some pieces of packages. We just remove that stuff, and we copied all the necessary files here. So now if you look to this comparison module, you can see that we removed reference to a package from this module, and then instead of putting everywhere p dot, we just remove p dot. So we modify a file just by removing things which are not supported in Icarus Verilog. So now once we do this, then like I together with Max Kudinov, we created in a directory common, we created the first we moved like everything about integer square root here, but now we created here a bunch of files like fadd, fdiv, and so on, and inside each file we just give it as an argument two floating point numbers. And by the way, I need to change this a little bit. I need to put include here to get this this flag. Yeah, so we put here like A, B, valid, result, so upstream valid, downstream valid, busy, and error. So error is for numbers like not a number and similar. And so we just instantiate volley FPU here, and that's it. So we essentially wrapped volley FPU into a series of modules which have valid interface, just like upstream valid and downstream valid, right? So like essentially we have the same thing as with a square root, but we are using here FPU. We have even a square root module, you see, but it's dealing not with integer numbers, but with IEEE floating point numbers. Okay, so now in our homework, so we created several tasks in our homework. And basically what I want you to do, I want you to create some new problems for the next homework with like pipelines and so on. They will show you what we created so far. So if you go into 0-3 sort floats, so first we show example a module which sorts two numbers. So there is a number A and B, and they one can be more than another one, and we need to change them, to change their order, to have first smaller and then larger. So we just sort two numbers. In order to do this, we instantiate module which compares two number, which is called f less or equal, and then we instantiate this module. And then we have code which is doing multiplexing. So it puts result 0 equal A, result 1 is equal B if A is less than B, and otherwise it's change their order. Okay. Now we put example in different styles. So we put those two numbers as an array, like as a two-dimensional array, and we just write it using 2D port. Okay. And now what student has to do, student has to sort three floats. So we show example how to sort two floats, and then student has to sort three floats. Okay. And now, in order to do this, we instantiate three instances of the same module. And then we put this code to just sort them in certain order, right? Now we have also test bench, and this test bench is checking different combinations. So this test bench has a task which just sorts numbers in this way, and we are using two special functions. One function is called bits to real, and another is called real to bits. And bits to real get a 64-bit double precision floating point number, and it gets a 64-bit vector and converts it into Verilog type real. So Verilog type real is a 64-bit floating point number, double precision. Okay. So here, but we are doing this sort for our reference, but actually in our test bench, we just instantiate this module, and we send it different combinations of numbers, and then we check whether this module sorts them properly. And we are also using some special numbers. So we're using number 0, infinity, not a number 1, 2, 3, 4, 5, 6, exponent 5, 8e. Why I put here 5, 6, e5? I should put e6. And this, I mean, e7. They put e5. Okay, this is fine. So now, the kind of familiar with a floating point number format, like IEEE 745. If you're not familiar, it's okay, because they are completely described in Wikipedia. So if you go to Wikipedia 745 wiki, yeah, so you can see in Wikipedia Wikipedia that floating point number. So there are like several formats, but our particular format looks okay, so this is 32-bit version. We are looking for 64. So let's put yeah, so 64-bit, double precision floating point format. Yeah. So you see that in our 64 bits, we have a bit number 63 as a sign, and then we have 11 bit for exponenta, and we have 52 bits like as a fraction, right? Now this tells like exactly how number is represented. But for the students, we can sort of allow to treating this format as a black box, and the only one knowledge student who does this exercise needs to have, that he needs to know that there are some special encoding for the numbers. First of all, there is special encoding for 0. So 0 is exponent is equal 0 and fraction is equal 0, and the sign can be the 0 or 1, which means that this floating point format has positive 0 and negative 0. And also there is a rule that if all bits in exponent are equal 1, then this number is the infinity, and all bits of fraction are equal 0. So this number is the infinity, and there is positive infinity and negative infinity. So you can read it in like any introductory text in like Harris and so on. And also there is such thing as not a number. So not a number is when all exponent bits are 1 and a fraction is not equal 0. This is called like not a number. And also there are denormalized numbers, which is exponent is equal 0 and the fraction bits are not 0. So you can get like any book like Harris and or like Patterson Hennessy, and it has a chapter on floating point numbers, or you can simply read Wikipedia. You can just Google IEEE 754 tutorial, and there are like tons of articles about this. Is like Geeks for Geeks explains it, but it is not necessary to know all the tiny details of IEEE floating point standard. I need to know some of those details because we have a floating point coprocessor in our GPU in Samsung, and I had to modify how like some cases of like optimized rounding is computed. So we do know we do have to know like little bit of theory of it, but usually you see so there is a zero, denormalized, infinity, not a number. But generally, in our examples, we treat floating point as a black boxes. Yeah. Now, uh, next task. Next task in our examples is to implement to sort floats using FSM. So suppose you have only one block of comparator, and you need to use a finite state machine to first like compare A and B, then compare A and C, then compare B and C, and then sort them in a certain order, like at the end. So now, like after this, the next question is how to implement discriminant of quadratic equation. So the end task is that create a series of exercises so that the students can be trained in building like arbitrary computing device with a given set of adder, multiplier, division module, square root, and comparator. And those submodules, they all have different latencies. So like add and multiply, they have latency of 2 clock cycles. And with square root, it's a variable latency, and with division, it's also variable latency, but it has a maximum latency. So if you want to build like pipeline unit, we can create a FIFO which can accommodate maximum latency um, like but actually for 100% pipeline unit, we need to either introduce back pressure or instantiate multiple dividers. Generally, you can play with different set of adders, multipliers, dividers, and square roots, and create blocks with a different area and bandwidths. And this is actually our task. So we want to train students to create finite state machines, pipelines, flow control, using this floating point blocks from a real CPU. And in my perspective, this is a good way to train because like instead of doing artificial examples like with like a traffic light controller, students are actually trained on realistic tasks applicable for the industry. So for CPU, GPU, for like AI accelerators and so on. Yeah. So what do you think about this so far?
Yes, really, that's a nice approach. Uh, it's good that the more you work with pipelines and flow charts. I mean flow controls. It's better that they get trained more with it, and it'll be easy for them to implement it in future.
Uh, yeah. So basically, I'm looking for several people, like including like me, you, maybe like somebody else, to implement series of such exercises. And one particular type of exercise I want to do is like one is solving quadratic equation, another is matrix transformation for GPU, like perspective transform. Yeah, perspective transform matrix. So let's see. Yeah, so you see in the GPU, we need to use so-called perspective transform, which just gets like 3D objects and puts them into perspective. So maybe we can create examples for this thing. Yeah, you see perspective transform. Yeah. So wait, let me see. Yeah, this is a good example because it's immediately applicable for GPU. GPU. Yeah, perspective projection matrix. So matrix for game developer. Yeah, GPU. Let's see. Yeah. So I'm looking for this specific picture. Yeah. So you see in the GPU, we need to convert 3D coordinates into coordinates in such projections space, and we can do this by a matrix multiplication on such matrix. So actually, in a GPU, we have task and fixed functions how we get coordinates and quickly apply this matrix for them. So if you create such example, it will be very realistic example. With like a pipeline. Um, yeah. So now like another example is McLaren is a series. Yeah. So yeah, this one. So in like in like first or second year college mathematics, yeah, there are like a Taylor series and um, McLaren series. So those are polynomials to compute different functions. And in order to compute, we can create a state machine which actually compute like such formula, and we can just uh, make this state machine with the higher or with the lower performance by using multiple number of like adders and multipliers and like other arithmetic blocks. So actually, I want to create a student exercise based on one of these series. So there are series to compute like sinus and yeah, like this ones to compute sinus and to compute like cosinus and like many other functions. So to compute like logarithm. Uh, yeah, so this is the table of the three of parametric functions, and we can convert every of them into a finite state machine. So basically, I want to create a series of such examples using arithmetic blocks from a value. So this is like a second thing. Third thing, what I'm interested to do is that Valley is a so Valley is a CPU with a static pipeline. So you have fetch, decode, execute, memory, write back, right? So you are doing everything in order. but I want to create examples and add to our example of a Tomasulo algorithm to so we get a stream of floating point instructions, so no branches, just like additions, multiplications, and so on. And we implement a scoreboard like in like CDC, the CDC scoreboard. Like I guess like probably many people implemented it already. CDC 6600 scoreboard. Yeah. 6600 style out of order scoreboard design. And also implement illustration for Tomasulo algorithm. So Tomasulo Verilog. Like many students, like I was interviewing in like previous couple of years, they actually saying that professor was doing Tomasulo algorithm with them, but I'm not sure. But when I was asking them whether they like tested it, how fast they trans comparing with static pipelines, they usually didn't test. But you see, you can find some examples of Tomasulo algorithms. I'm not sure whether this is a real example. No, this is not. This is like mother or something. What is this? Looks like a state machine. Anyway, but anyway, in the Tomasulo algorithm is described in like various like textbooks, so you probably went through it, computer architecture, and like I want to use those blocks and just create illustration for Tomasulo algorithm. So this is another kind of tasks. So if you can try using Valley. Yeah, if you can try using Valley for this purpose, this would be very useful to implement, let's say, McLaren series, like one of McLaren series of one of like McLaren series listed here and implemented like as an FSM. Yeah, and we can put it as a part of like next series of homework exercises, like in homework 4. And we can also create a pipelined version of so we can use we can put a computing unit to which is like a pipelined computing unit with a back pressure to do to compute roots of quadratic equations. So you can just like think about it and then like come back to me and tell what kind of computing unit you want to implement, because I think this is a much easier task than to port Valley to some FPGA right now. Like so, it's up to you, because you see, when we are trying to port Valley, we are going to solve different problems with like memory wrappers and with scripts to build it and so on. So this like a lot of hassle, but this one is a much smaller and very well defined task, I think, right? Yeah. So you can think about it and just like tell me what kind of example you want to create, and then we can create some example and add it to this homework number 4. Yeah.
So basically, you're just using the components from the Wali and trying to implement
Yeah.
the quadratic equations.
Yeah.
Yeah.
So yeah. You can start from discriminant, which is by the way not implemented yet. So
Okay.
we put it in the homework, but this is not implemented here. Just a mock-up. So here there is no RTL code. You just need to put RTL code here. So you can start from this one. Yeah.
Okay. So the others are completed, right?
Yeah,
From the previous
sort is
exercise.
completed. So sorting is
Okay.
completed. So sorting FSM, you can use sorting FSM as an example. Or
Yeah,
you can
just
put
to see
like
how it's being used.
FSM
Yeah.
in your style, yeah. Or you can put FSM in your style, and then like the very first task is actually very well defined. You can just implement FSM for floating point discriminant. So let's start from this one because this is very well defined, right?
Okay.
So you just need to implement FSM which computes this number, and you can. You can actually do it in a kind of smart way. So you can use the fact that a multiplication unit is a pipeline. So you can, in first clock cycle, you can put A and C arguments, and second clock cycle, you can put B arguments to compute B square. And then once you compute B square, like after this result of AC multiplication, and then you need to multiply it by 4. And once you multiply it by 4, you subtract b square minus 4ac. So like totally you need to do it in FSM in like several steps. Yeah. So first you can try to implement this thing. Yeah. And do you have access to private repository? To this one, homework private, so I don't remember. But in any
No.
case, whether you have or not, you can use public right now. Or if you don't, I can give you access to this repository. So wait a second, I'm on this list. Yeah, so give me your email. I will add you to this repository. But so let me get in a second. Yeah, but this is like first task. This task is actually pretty well defined. Okay, so let's see. So you did contribution to this one, right?
Yeah.
So it was a pipelines 2, or which one was it?
I
Pipelines
think it's
1,
the square
pipeline.
root pipeline, square root a square plus b square plus c square, and then
A second. Let's just find it. Okay, so this is power 5.
I think it was
Where is it?
yeah, no, not this one.
Yeah, it was in different places. So let's find it.
Yeah.
Pipelines 2. Here at the unfinished. Oh, wait a second. Was it in this repository? Yeah. It was 04 arithmetics and pipelining. Yes, it was in
Yeah.
homework, right?
Yeah, homework.
Arithmetics and pipelining.
Yeah, this is the one.
Yeah, 004. Yes,
Mm.
this one. Yeah, okay, good. Yeah. So this means that you have already access to this repository, or do you?
No,
To the
I actually cloned the
wait.
public
This
link.
was this was in um, hmm? Did you check in only into public?
Yeah, I did not have access to private. So whatever I
Really?
did, I
One
made
second.
my project as private and shared that link to you.
I already forgot it. 1 second. Phone pipeline. No, but this one has only valid. It doesn't have. It doesn't have ready.
Yeah, but the one that I worked on
Yeah.
was with valid ready
You implemented.
credit based.
Ah, yeah,
I
credit
the
base.
one that I
Where is?
worked was with valid ready and credit based flow control.
Uh-huh.
So I implemented.
1 second. Yeah, this is. Yeah, this is not here. So let's find it. Uh,
It was in system Verilog Homeworks, but uh,
so you put it in system Verilog homework, right?
no, I did not initiate a pull request for it. So it was like a homework that I did, and I shared my private repository with you for you to verify.
Okay. But I didn't integrate it here, right?
No,
Okay. This is fine. So we can integrate it now. So I will just give you access to private repository, and then you can integrate it here. So
so
okay. So can you share it with me again?
okay. Um,
Wait. So can you give me your email in chat?
yes.
Okay.
Yes,
Yeah.
that's the one that I
Okay.
use for
So let's
GitHub.
yeah. So let me just put it here. So basically, I'm adding you here like as a member, and then what I recommend to do is that you have. 1 second. Let me. Why it doesn't allow me to press?
Mhm.
Invite member. Okay. Uh, Because sometimes when I'm on Zoom, it does not allow me to press buttons.
Okay.
Okay, let me close this. Mm, Yeah, so what you can do is you can clone public, you can clone private repository as a private in your area. So like private clones into private, and then you can give me pull request with your additional homework. So we can incorporate it there, and then you can start in the same way on a new examples. But let's first do it with system Verilog Homework private. Yeah, like I guess I need to turn off Zoom in order to do this because Zoom does not allow me to press buttons on the screen for some reason. Maybe I should stop video or something. I'm not sure. Anyway, I will send you an invitation here, like later on. See, because it does not allow me. Okay, I will send you this invitation later on, and so that first you will clone this private repository and try to make me a pull request, so I can incorporate it. Yeah, but please make sure not to share it as a public. And also, let's do everything through pull request, so that because it's very easy once you have like access to the private repository, it's very easy to mix up something here, and this is what I want to avoid. So okay, yeah. So now you can actually look to. You can look to this example. They're now like available in public too. And just first you implement discriminant, and they will review it, and we will integrate it into public and private. And once you implement for discriminants, then we will implement like other mathematical blocks. Yeah, and basically, I think this is kind of good innovation in education, because by using blocks from a real CPU, and CPU which is just created in like a Harvey Mudd in Southern California, we actually show how students can be trained on computer architecture and RTL at the same time. So maybe we can like publish article about this or something, and put it somewhere. Yeah. Okay. So I think that we kind of discussed it. So do you have any questions about it?
Not as of now, Yuri.
Okay.
But I think I have to fork your private repository.
Yes. So once I send you
Yeah.
invitation, you will fork my private repository, and then you can put as a pull request what you did with the integer square root. I will integrate it into a repository, and after this you can start working on like other on this discriminant
Discriminant,
problem.
yeah.
Yeah,
Yeah,
yeah.
I try to just run the other projects in that using the Wally CPU just to get
Yes, yeah.
flow of it.
Just also test how current exercises are
Yeah.
implemented. If you have questions,
Questions, yeah, I'll get back to you.
let me know. Yeah.
Yeah,
Okay,
sure. You.
okay. Thank you. So we discuss and talk to you later. Yeah.
Yeah, thank you.
So like I will now do this Apple port in here. Yeah. Okay.
Sure.
So thank you. Bye bye. Yeah.
Bye.
I use this. Leave and